Hello everyone, and welcome to the Toy Car Post Lab. So in this lab you use a little car and you measured the distance it went in certain amounts of time, right? Controlling the time, measuring the resulting distance, and so you made a graph eventually of distance versus time, which hopefully looked basically like this. Right? A graph which is both linear and contains 0, 0. Of course, hopefully by now you know that when you graph two variables and they result in a graph which is both linear and contains 0, 0, the relationship between those variables is proportional. So if you let the car run for twice as long, it basically went twice as far. If you let it run 3 times as long, it basically went 3 times as far. And you probably can even see that in your data if you check out your data table. Right, so a nice direct proportion there. We can, of course, create a y equals mx plus b math model out of this, because it's a linear graph. The y variable is what we graph on the vertical axis, which is, of course, distance, for which I am going to use the symbol d. D for distance. I've seen it sometimes as a capital D, lowercase d. Doesn't really matter, I guess. But d for distance. That equals your slope. Now, unlike some of the other labs we've done, I wasn't quite sure of what your slope would be. It kind of depended on how your car was set up and maybe how strong the batteries in your car were at the time. So I'm just going to put in a number symbol. You, of course, have hopefully written in your actual slope, right? Whatever you actually got out of the lab. Units, though, are the same regardless. We find a slope by doing rise over run, and so that's how we find the units. Units of rise, centimeters. Units of run, seconds. One of the more important things in this lab is, what does that actually mean? What does that tell you about your car? And so I've asked you to write a for every statement, right, for this. Hopefully you're getting a little better at these. So usually you say something like, for every 1 second the car runs, it moves an additional that many centimeters. Whatever it was, right? So if your slope was, say, 3 centimeters per second, it would mean that every second that goes by, your car travels an additional 3 centimeters. It's how far your car goes every second that goes by. Now that's actually a quantity that we are familiar with, and in a moment we'll give it a name, right, and a symbol so that we can use it, right, to describe motion. Okay, but for now, hopefully that for every statement kind of makes sense here. The x variable is what we graph on the horizontal axis, which is of course the time, so I'm going to put in a t. And the y-intercept? Well, logically it should be 0, 0, because after all, the way we did this lab, right, you actually had a 0 time at your first block that you put down on the floor, and so it really should have been a good 0, 0 point, right? But hopefully you also, even though you might have gotten a small y-intercept when you did your linear regression, right? If you take 5% of your largest distance, it's going to be much bigger than your y-intercept. Remember, you can ignore the positive or negative, which means that since the y-intercept is smaller than 5% of your largest y, you can say that it's negligible. We can neglect it, so it's basically 0. Right? And again, that kind of makes sense, right? Which tells us that when the time is 0, the distance should have been 0. Again, that's kind of how we did the lab, right? We'll take a look at what happens if that's not true, right, in an activity that we're going to do tomorrow. All right, but for now, 0, 0. And of course, you don't have to add 0. So this becomes basically your specific math model with your particular slope. Now, one of the questions I asked on the sheet were sources of error. And there's a few places that you could make error in this lab. Some of your cars might have been more one-dimensional than others. In other words, some of them probably went in pretty straight lines, and some of them might have had a bit of a curve. And if yours had a bit of a curve, you kind of had to try to measure around the curve, which throws it off a little bit. You're going to see in the next activity, we're going to actually put the little car on a track, and therefore it will go in a perfectly straight line because the track kind of holds it on, right? Another source of error, and probably the biggest source of error, is how good did you do at placing the blocks at exactly the right time, right, when the metronome clicked, and how good were you at placing them at the exact same place on the car every time, whatever place you chose, right? Say if you chose the front wheel, were you really putting it down where the front wheel was, and were you really matching it with that click on your metronome? Hopefully you got better at it. It's why we did 3 trials and averaged it, right? But still, that's probably one of the bigger sources of error, right? Notice how those are specific, right? It's not just human error. Yes, it's always human error, right? But we need things that are more specific to show that you've actually, thought a little bit about how the lab can be improved or how you could get more data. Okay, so let's talk about that slope. It was, again, how many centimeters your car traveled every second that goes by. Does that sound like something you've heard of before? Well, let's change the units a bit, because you probably haven't heard of it in centimeters per second. What if instead of centimeters, we use distance units like miles? What if instead of seconds, we use time units like hours? Now we'd have a quantity that would tell us how many miles you went every hour that went by. Does that sound like something you've heard of before? Yes, that is what we call the speed. All right, speed is what we call this quantity that we just found. It's denoted in an equation by a lowercase v, not a capital. That's usually volume or voltage or other things. All right, it's a lowercase v. You might wonder, why is speed a lowercase v? We'll get there, but it's going to take us a day or two to get there. Okay, just suffice it to say, this is the typical symbol. You don't really see it called an S very often. It's usually going to be a v. So operationally, we can now define speed as the slope of a graph of distance versus time. Exactly what we found here in the lab. If we want to be a little more generic, right, we can just basically say it's how fast an object is moving. And now that we know the term and we know what it means, well, now we can use that term. Right? Some of you might have been wanting to use it a little earlier in the pre-lab, right? But I wouldn't let you use it then because we hadn't defined it yet. But now that we understand what it means, and what it tells us about the motion of an object, whether it be a toy car or a real car or an airplane or anything that moves, right, we can now use this terminology. So, if this is our specific math model, if instead of using your specific speed that you had, if we plug in the symbol v, we get a general math model for this motion. Distance is speed times time. Or you could solve this, right? Speed is distance over time. Probably not a big shock to you. In math class, you might have even heard this as distance is rate times time, although I really hate rate. It's a math thing, right? It's more specifically a speed here. But this is the equation that we can then use to make predictions. But we do have to be careful about something here. This is not just any speed. It's a very special speed. Why is it special? Because look at the graph that resulted from this motion. Note that you got a linear graph. Well, what's special about the slope of a linear graph? What has to be true about the slope for your graph to be linear instead of curved? Hopefully you're saying to yourself, well, if it's a linear graph, my slope down here is the same as my slope here is the same as my slope here. In other words, linear graphs have constant slopes. And since we just defined the slope of this distance time graph to be the speed, that means this is an equation for one-dimensional constant speed motion. Right? Since the slope is constant, the speed has to be constant. So don't get overexcited about this math model, because it really only applies to a very specific motion, which is one-dimensional, straight lines, right? Or something we can approximate to straight lines, where the speed doesn't change. If your object is speeding up or slowing down, well, that's a whole different thing. And we're going to, 2 units from now, we're going to describe one special case of that happening right? And we're going to need a whole different set of equations and different graphs, but we'll get there, right? In this unit, we're going to focus on one-dimensional constant speeds. So I hope you enjoyed this toy car post lab.